Continuing on our integration techniques. This is missing an S, I just noticed. We have integration by partial fractions. So this is kind of annoying me. I'm going to move this down. And then I'm going to move this down. And this. Oh, that is not in line at all. There we go. Yeah, just space better. Okay, integration techniques, we're talking about partial fractions. Partial fractions, not my favorite, kind of tedious, but useful, so. Essentially, we have the issue of not being able to integrate some certain fractions of, let's see. I'm gonna start off with a simple one, perhaps. X squared plus 2x minus 1 over 2x cubed plus 3x squared minus 2x. Okay, so our issue is that we don't know how to integrate that, because we can't sub the bottom and have it be equal. Let me do this right. We can't sub the bottom and have it equal to the numerator, and we can't sub the numerator and have it equal to the denominator. So what we're going to do is we're going to split this into a bunch of little fractions, because this is essentially a bunch of fractions, this fraction, this fraction, this fraction, with the common denominator of this. So we're just going to split it back into its fraction form, and then we can take the integral of each of them separately. So the way we do that is we're first going to factor the denominator. Okay, so I'll label the steps as we go. Okay, factor denominator. So we have 2x cubed plus 3x squared minus 2x. So this is equal to, we can take out an x from these two. So this is called factor by grouping, because we're grouping this and factoring from what's in there. So we're left with a 2x squared plus 3x. And then a minus 2. Oh, wait. This has an x too, so I don't even need to do that. It's just like this. So I didn't see my own handwriting. So it's not factoring by grouping. Just factor it regular. And then this, we're going to try to factor. So 2x times an x. We need two numbers that multiply to this and add up to 3. So okay, so basically we can't factor that. So now we're going to do some cheeky thing. So 3x is the same thing as 4x minus x, and then we have our negative minus 2 on the end. And this we can factor again into 2x, and then this becomes 1 plus 2. Wait, no. This is an x squared. So it becomes x plus 2. And then we're going to factor a negative 1 out there, so we have x plus 2 here. So that's like, it feels kind of like cheating, but hey, it works. And then you see how this is an x plus 2 and this is an x plus 2? So we're going to factor an x plus 2 out of this term, this term, and this term. So what we get is x, and we have our x plus 2, and then we have our 2x minus 1 from this, and this minus 1 right there. Invisible minus 1. So I guess I don't need the brackets here. And I'm just going to move everything closer together. What is this line? Oh, probably a bracket. Okay, so this is our factored form of this denominator. Now, I know this part right here where we made this into 4x minus x was kind of cheesy, but you're generally not going to do this. I guess I just chose a difficult first problem. But the point is, you want to factor the denominator. Most of the time, no, basically all the time, it's going to be an easy thing to factor because College Board is testing you on your knowledge of the calculus, not your knowledge of how to factor this. And the final will be similar to College Board because it's like a mock AP test, essentially. So we have it factored. Now the next step is each of these are the denominators of one fraction. So if I draw a line here, actually I'll just put it under it. So we're going to have the numerators be called some, just a, b, and c. So this goes up to here, and a goes over this first factor, and then b goes over the second, and c goes over the third. And now the reason this works is because these multiplied together give you this. And you have to multiply these together to get a common denominator so that you can add all of the numerators together. Oh, it's 2x minus 1. Okay. So again, when you multiply these together to get a common denominator and add up all the numerators, you get this numerator with this denominator. So that's why this is equal to that original function, which is x squared plus 2x minus 1 over 2x cubed plus 3x squared minus 2x. Okay, because this is just the factored form of this. And these numbers that we don't know yet, but we're going to find out, will become this. Okay, I hope that makes sense. So we're going to figure out what numbers will make it equal to this. So the way we do that is we take each of our letters up here, and we're just going to write them A, B, C. And then we're multiplying them to whichever denominator it does not have. So we have a to the a times, we have an x with the a, but we don't have the x plus 2 or the 2x minus 1. So we're going to multiply by an x plus 2 and a 2x minus 1. And the reason we do this is because when we're trying to make common denominators, we're going to multiply this by an x plus 2 over an x plus 2. And then we're also going to multiply it by the 2x minus 1 and over 2x minus 1. So then this denominator has all of these factors together. And remember, all those factors together give us the denominator. So now we just need to multiply, we just need to find the numerator part, which is this. That's the numerator. Then we're doing the same with the other ones. So this b is missing this factor and this factor, so we're going to give it an x and a 2x minus 1. And then the c is missing this factor and this factor, so we're going to give it an x and an x plus 2. So now, to determine what each letter is, we want to isolate it essentially. So we're going to plug in a number that will get rid of this entire factor, both of them. So we only get an a number. So you see how this x, both of these b's have an x? I mean, this b and c both have an x. Well, if we plug in 0 for x, that would make this, in both of these, equal 0, which takes them out of the equation, which is good. That's what we want. So we can focus solely on a. So if we plug in a 0 here and here, we get 2 times 0 into there. 2 times -1, which is -2. And then we have our factor of a, so -2a. And then we plug in the 0 into this numerator as well. So essentially what we're doing is we're setting this a part equal to this numerator. See that? And this a came from there. And remember, I'm going to say it again, just to make sure. These two factors came from us trying to make common denominators with these two fractions. And when we make common denominator, then we can add these all together, and that'll become this. So this is us like figuring out what a to plug in will give us this part of the function, the numerator. So -2a. So when we plug in a 0 here, we get 0. Plug in a 0 here, we get 0. And we're left with a -1. So -2a equals -1. A equals 1/2. Just moving the 2 over there. Now we're going to do something that can get rid of the a and the c, so we focus only on b. So I see both a and c have a factor of x plus 2, so if I plug in a -2, it'll make both of these 0 and get rid of that out of the equation. So that's what I want. So now I'm going to plug in a -2 to x and a -2 here. So I get -2, this is -2 times -5, which is 10. So I get 10b. And then I plug in a -2 here, that's 4. Plug in a -2 here, that's -4. And then I have a -1. So 4 minus 4 minus 1 is -1. So our b equals -1/10. And then I want to get rid of a and b. And I see they both have a factor of 2x minus 1. So if I plug in a 1/2 into both of them, it'll make everything go to 0 for a and b. So I put in 1/2 here and here as well. So this is 1/2, 5 halves. So that's 6 halves, so that's 3c. And then I plug in a 1/2 here. 1/2, that's 1/4. 1/2 here, that's 1 minus 1. So those cancel out, and I'm left with 1/4. One half. 2 is the same thing as 4/2, plus 1/2 is 5/2. So this becomes 5/2. Oh, wait, and then this is 1/2, and I'm multiplying them. So this is actually 5, oh, I messed that up. Oopsies. 5/4. See, I was getting confused. And then this is the 1/4. Okay. Whoops. I added them by accident. These two. Okay, so that's the correct part. And then c equals multiply by 4/5, so the 4's cancel out. You get 1/5. Okay. So now we know what our a, b, and c's are. Let me highlight them, because it's getting kind of messy here. So this is important. That's important. And now we're going to plug these into our A, B, and C. So, and this is what's going to go on the inside of our integral. Okay, so let's just write the integral first. I'm going to write equals because this is equal. Our A was 1/2. Okay, I think I need to make this integral bigger. I'll keep the arrow. So 1/2 over x plus, or actually minus 1/10, because this is a negative, over x plus 2 from here, plus 1/5 over 2x minus 1 dx. So that is our integral. So this is equal to this. I just wrote it in a different way. Okay, so before we move on to actually integrating, let us recap quickly. See, this is why it's not my favorite, because it's very tedious. So what did we do? We have our denominator, or we recognize that this is a fraction that we don't know how to integrate using like substitutions, and we can't use partial, what is this called? Parts. We can't use parts to differentiate, so we have to use this new technique called partial fractions. So these are all fractions that are a part of this big function. They all make up that big function. That's why it's called partial fractions, because these are partial of that. So what we did is we factored out the denominator, and then we know that these three numbers, these mystery A, B, and C numerators, added together after you do all the common denominatoring, making common denominators, you get this. So we just had to figure out what A, B, and C were. To figure out A, B, and C, you multiply it to the denominator's factors that it does not have. So B doesn't have this, so you multiply it to those. C doesn't have these, so you multiply C to those. And then you plug in a number that will get rid of two of them at a time, so you can just focus on one variable. And then you also plug it into the numerator, so you can figure out what that variable equals. Then once you figure out your variables, you just put them back into the fractions. And those fractions are what goes on the inside of your integral. Now this is nicer because we do know how to take the integral of these smaller fractions, because there's only an x in there. And remember, I went over it in a previous section, derivative of okay, I don't know where it is, but derivative of something over just a singular x to the first degree. Okay? So remember, when you're integrating something over x to the first degree, this 1/2, 1/10, and 1/5, or negative 1/10, and 1/5, those are just constants, so you can just put them in the front. And then you're left with, like, this becomes 1 over x when you put the 1/2 in the front. So the integral of 1 over x is the natural log of absolute value of x. Okay, so you want to remember the integral of 1 over x is the absolute value of that in a natural log. So now we have, I'm going to move the negative 1/10 into the front, and then integral of this. So if you imagine this x plus 2 is your u, then you're just integrating u, and then so integral of 1 over u would be natural log of u, and our u is the x plus 2. And then you would put a du, but the derivative of this is just 1, so you don't really need a du there. Let me make my eraser smaller. Okay. And then you have our 1/5 move into the front. Now pretend that this 2x minus 1 is a u. So you want to integrate the 1 over u, which is natural log absolute value of u, and our u is the 2x plus 1. And then we want to chain rule it. The chain rule of 2x minus 1 is a 2. So I'm actually just going to put the 2 in the front here with the 1/5 because it's a constant. So those mini u substitutions, you want to be able to do them in your head or like do very minimal work for them. So just write like a u there to remind you that it's going to be like 1 over u, and then you integrate it with the chain rule. So because otherwise you're going to be doing a lot of work. And then as always, this is an indefinite integral, so you want a plus c at the end. And then that is your differentiation by partial fractions. That's your answer. Very long, I know. I should highlight the answers from these ones as well. Okay. Okay, those are partial fractions. So remember, I'm going to recap one more time, because repetition. You have a fraction that you don't know how to integrate. We want to split it back up into little fractions. So to do that, we first have to factor the denominator, okay? So step 1, I'm going to write step 1 over here. Factor denominator. So that's step 1. I'm going to move this over. So this is 1 here, factoring the denominator. Step 2 is writing them as fractions. Step 2, write as individual fractions. So all you're doing is you're taking one factor and putting an a over it. You're taking the next factor, put a b over it. Taking the next factor, put a c over it. And remember, this is the denominator, so what you're finding is going to be in the numerator. Okay? So you want to split them up, write them as fractions. And then you're going to solve for a, b, and c. That's step 3. Here, I'll put it right here. 3. Solve for a, b, c. And there could be more, it could be less. It could just be like 2 fractions, it could be like 4 fractions. Just solve for the missing variables. And remember, you do that by multiplying your variable, so your a, b, and c, by the factors that it does not have in its fraction. So this a has this a has the x, but it doesn't have this x plus 2 and the 2x minus 1. So you want to multiply the a by the x plus 2 and 2x minus 1. And then remember, to solve as well, you want to eliminate 2 at a time and focus on one variable. So you plug in an x, you can choose any x that will eliminate 2 of the variables at a time. And then you plug in that same x into all of these and into this numerator. So then all that simplifies to this. And then you just solve for your a. So you do that for all 3 of them. And then step 4 would be to write as an integral and integrate. So write as an integral and integrate. So once you find your a, b, and c, put them into their respective spots, and then integrate. Remember, it's important to know how to integrate 1 over x, or 1 over u. Okay, these are like mini u substitutions. So don't forget your absolute value bars. And these are just constants, so you can just put them out in the front here. And then if you have to do a u sub, don't forget to chain rule, like this 2 here. And don't forget your plus c. So that's integration by parts. By partial fractions. Okay, the very last thing I'm going to talk about, because it's pretty short, are improper integrals. So these are just integrals that have an infinity in its bound, like that. So this is improper because, well, you can't have infinity in the bound. So what it looks like is you're looking for an infinite area, essentially. So if I have this graph, and this is my, here, let me draw it better. That's my function, and I'm going from a to infinity. So I start here, and it doesn't end though, so I'm looking for this entire area. And so on. And this is what leads you into series. But I already made videos on that, so you can watch those if you want. And the way you get around an improper integral is that you write the infinity as a limit instead, because we can have limits. So you just change this into like a t approaching that infinity. We want it to be some variable that is not in our function. And then we have our regular, we can just put everything back. So now it looks like it's going to a finite number. So what you do to solve this is you do the integral first, and then you take the limit as t approaches infinity. So that's how you get around doing an improper integral. So this is what leads you into convergence and divergence. So if this was the graph, I'm just going to use this as an example. If this was the graph of 1 over x, then if you remember from our series, from like a to infinity of 1 over x dx, this is going to diverge because this is a divergent p series, or a harmonic series. That's also what it calls. Diverges. And the reason is because this denominator does not increase fast enough to make this fraction approach 0 as you go out towards infinity. But if we have a different graph, like this one, and let's say this is like this. Yes. And this graph is 1 over x squared. And we start at a here, just like the other one. So we're finding this area now. But you see how it gets like really tiny out here? So this one converges from a to infinity of 1 over x squared dx. Converges. Because this 1 over x squared, the x values increase fast enough for this fraction to approach 0. See how it's getting very close to this x-axis 0 line? So that's how we know it converges. It converges to a number, which is 0 here. And this one doesn't converge because it doesn't decrease fast enough. So this area is infinite. So I'm gonna write that actually. Infinite area. But this one has a finite area because eventually it converges to 0, so you can calculate the area. But that's starting to get into series. So just the idea is you can't have an infinity in the bound, so we rewrite it using a limit and replace the infinity with a variable to get around that. And then to solve this, do the integral first, and then the limit. Okay, that's all about integrals.